Well, it's time for the next presentation.
Excuse me.
Isotopic tracers and catalytic kinetic studies in oxides by Professor Joe Hightower.
Well, thank you very much, Bert. I think we all owe Bert a vote of thanks for getting this thing organized, perhaps under less than ideal situations here. We hope that Professor Farkas, Dr. Farkas, does come shortly. What I would like to talk about today, since Dr. Farkas was one of my idols, I've actually had several idols, some of whom are here today. So I appreciate your mentoring. But I decided to talk about isotopic tracers and catalysis. And after I wrote the title down, then I remembered that there are people who have written books on this subject who are here today. And then I thought I'd talk about kinetic studies on oxides. I'll be talking about acids and bases. And again, books have been written by people in the audience today. So I'm treading on very dangerous ground. I realize that. So I'm going to use this as an opportunity to review some of the material that we've gone over at Rice University for the last several years. I listed some of the people who worked with me on this and some of the funding sources. We appreciate very much that material. I also remember very well the wonderful wit and the superb science of Dr. Farkas. So those are things that have meant a lot to me. Well, the catalysts that I'll be talking about today can be divided into two categories. We have solid acids catalysts, and again, the title of a book could have copied this material from that book. I'll be talking about an old silica alumina amorphous catalyst, M46, and I'm sure that that would be a catalyst that many of us older people have used, and Dr. Farkas certainly would recognize that. It's an amorphous material, has about 250 square meters per gram surface area. Then some silica magnesia, we won't say too much about that, and then there's an acidified silica aluminophosphate that was made in our laboratories by a union carbide patent. It's crystalline material. And we have also used some of the Mobil's acid ZSM5 catalyst. And finally, a synthetic mica montmorillonite that was prepared by Baroid Division of M&L Industries. I'm just putting these up here to show you because the work that I'll be talking about has actually come from using several of those, and I may or may not identify them as we go along. But that's the kind of material. All of those are the solid acids. Now, when we get down to some oxidation reduction or oxidative dehydrogenation, we will be looking at spinel catalysts, mainly magnesium ferrite, but there are also some other ferrites that may have cobalt, calcium, nickel, zinc, etc., in the place of the magnesium. Now, the test reactions that I want to focus on are really three of them. Work that has been, some of it done in the range of 20 years ago or so at Rice. Cumene dealkylation, N-butene isomerization, and then the production of butadiene from butenes over an oxidative dehydrogenation ferrite catalyst. Now, the main thing I want to do is to focus on the use of isotopic tracers, primarily hydrogen and deuterium to be the materials that we'll talk about. Now, in the case of cumene dealkylation, for those of you who may not be terribly familiar with this, this is an old classic reaction that's been used as a screening reaction, a preliminary screening reaction for testing acid catalysts. If a catalyst won't dealkylate cumene, throw it away. It's one of the first things that one would do. And basically what we're talking about is take the reaction taking place over acid sites. One of the big arguments in the literature has been for many, many years is whether or not these acids are Lewis sites, electron acceptors, or are they Bronsted proton addition sites. We thought that one way of testing this might be to use a microcatalytic pulse reactor and use deuterium tracers. let me just go through the mechanism if I can first. It was proposed that if these sites are active, that one has the proton or deuteron attacking the benzene ring or at the point of alkylation. And then you have the formation of propylene, and finally the removal of this hydrogen to the surface. And if that's true, then the hydrogen that originally was on the surface should end up in the benzene. But of course, if one starts off with a catalyst that contains deuterium, then this would be a monodeutyrated benzene. Now, the type of reactor was a microcatalytic reactor, which is just a gas chromatograph. It has a detector, helium stream, and an injector. The only difference is now we have a small amount of catalyst that we can pass a pulse of cumene or whatever over the catalyst, and then as the products are separated, and in this case, the separation, we've already heard a lot about gas chromatography today, is really quite clean, with propylene, benzene, and unreacted cumene products. And it's possible then to collect, say, the benzene product and put that into a mass spectrometer and look for the presence of deuterium. Now, what we expected to find was that we would have benzene with essentially 100% of D1 species, monodeutyrated. And so we set up the experiment in such a way that there was plenty of deuteriums and a very small amount of cumene that was passed in pulses over the catalyst. What was observed was, in fact, some monodeutyrated benzene. That's fine. There was also some benzene that had no deuterium in it. Well, that's okay, because once this peak or this deuterium had been used and replaced with hydrogen, then the next time it's used, it would pick up a hydrogen. So that didn't bother us. But the problem was there was also material with 2 deuteriums in it. There was some material with 3, 4, all the way out to D6. And that did not make sense by this kind of mechanism. This was, by the way, an experiment that we thought we could set up in the morning, because it was very easy, as Al has told us, to set up a gas chromatograph and carry these things out. We could set the equipment up in the morning, collect the results in the afternoon, write the paper that evening, and if we were lucky, get it to the downtown post office by midnight, get it in as a note. It didn't quite work that way. So we thought, well, okay, now let's do the experiment again, and this time collect the propene peak and see if there's any deuterium. There should not be any, according to this mechanism. But when we looked at it, there was deuterium all over the propylene. And in fact, it looked very similar to benzene. Well, under these conditions, which amounted to about 350 degrees centigrade, a contact time or space-time of about 1 second, and there was a fractional conversion of the cumene, which was approximately 50%. So that means half of the cumene put in came out unreacted. Now, of course, there won't be any deuterium in the unreacted cumene. Well, when this was tested, much to our chagrin, there was deuterium in the cumene. And it looked very much like the deuterium distribution in the benzene and the propene, only not quite as much. It was limited to only 5, whereas here we had all the way up to D6 and D6 on both of these products. We'll come back to that in just a minute. So this frustrated us quite a bit. But it looked like that what was happening was that all of the hydrogen atoms, at least many of the hydrogen atoms, in all of the products and the reactants were in fact scrambled to statistical equilibrium with all of the deuteriums that were on the surface. And so we had now taken this experiment and turned it into an undergraduate experiment at Rice. I think I've said before, whenever one does an experiment that does not turn out the way that it's supposed to, there's only one thing to do with it in an educational institution. That's turned it into an undergraduate laboratory experiment. But this one really did turn out to be quite interesting. Now, one of the things that we'd like to know is how many hydrogen atoms are there possibly on the surface? And we can do that by exchanging those with deuterated benzene. and in fact I have an error here, this should be D6. And as it happens, and I'll show this some data in just a minute, that only the benzene hydrogens, or the alkyl hydrogen, the aryl hydrogens, and all of the benzene hydrogens and the propene hydrogens were exchanging. These hydrogens on the alkyl group did not exchange at all under these conditions. So if one puts a pulse, say, of deuterated benzene over the catalyst under the same conditions where one has, say, 50% alkylation, and let's just assume that we adjust the catalyst to the pulse size ratio, where we get on the average approximately 3 of these hydrogens or deuteriums being replaced with hydrogen. In the first pulse that we put over, we would be able to see then an average composition of the benzene. And by the way, the benzene itself was not cracked at all under these conditions. These are very mild cracking conditions. There were 3 hydrogens and 3 deuteriums in the benzene. Now, if we take another pulse, a second pulse, say, under the same conditions, it will also exchange 3. Perhaps these 3, these 2, and maybe this one in the middle. It's already exchanged once before. And one would have then an H2D4. And finally, if we like, we could use a black one and have, or brown, I guess, again, a third pulse might exchange this one in the middle, maybe way over here, and again this one. And one would have perhaps an H1D5 species coming out of the reactor. So if one now goes through and plots the number of atoms that are exchanged as a function of pulse number of the deuterated benzene, what I've illustrated here, the first pulse would have exchanged 3 atoms on the average. The second pulse, 2. The next one, 1. Actually, what happens is, of course, that these come down exponentially. And one can tell how many are exchanging. But we're really not interested in how many exchange per molecule. What we'd like to know is the cumulative number. That cumulative number we could call sigma, or sigma infinity. Now, if we know how many molecules that are put in each pulse, and we know on the average how many atoms have exchanged, then we can multiply those, and for the first pulse we'll have a number like this, second pulse, third, and this will approach some value that will be sigma infinity, the total number of hydrogens that were on the surface that we're hoping to relate back to active sites. Now, this is a nonlinear plot, and chemical engineers are not really happy with nonlinear plots. Chemists seem to do all right with them, but engineers, it drives them up the wall. So what one can do with reasonable assumptions is to invert the sigma, the cumulative number of atoms, and invert the pulse numbers such that the last pulse out here that we measured becomes, or I'm sorry, the first pulse that we put in becomes the last pulse on the linear plot. So there would be a point here, etc. And this turns out to be a dead linear plot that has an intercept of 1 over sigma infinity. And that's the number that we were looking at. So it's possible then to use this as a technique for measuring what may be the active sites. Now, how do we know they're active sites? Because obviously up here at the top, they exchange. So we really don't have the kind of experiment that we hoped to have in this. Well, it turns out we were carrying out the experiments wrong, because this exchange reaction is extremely fast, and it does go to statistical equilibrium. But the dealkylation reaction has a rather reasonably high activation energy. So if we go to high temperatures, very fast space velocity, then it is possible to observe make this observation where we have dominantly the D1 species. And so the fast exchange reaction now has continued at the same rate, but the dealkylation reaction is much faster and has finally overtaken the exchange reaction. We can't get there. So we're convinced that in general, these sites are the active sites that are used for that reaction. Now also, this kind of plot over here would not have occurred were all of these sites not reasonably easily exchangeable. To the same degree. We didn't have different kinds of exchangeability with the deuterium. So I want to follow up on that a little bit by looking at how the exchange occurs in a stepwise condition, even though it's very fast. Remember, the contact time is 1 second, and all of this chemistry occurs. What happens is when one starts with a C6D6 material, if one put this into a batch reactor with the catalyst, and all of a sudden said begin to exchange, as a function of time, we would have the deuterated D6 benzene falling off as the exchange occurred. Then we would have the first product formed would be the mono-exchanged D5 species, which would come up and go through a maximum. And then the D4 would probably begin with an zero slope, go through an inflection point, and then come down, D3, etc. So this is what we would expect to have in a batch reactor. But obviously this is not a batch reactor, it's a pulse reactor. So instead of measuring time down here, the first pulse that went over saw the most exchange, and we would correlate that with the longest time. And so somewhere out here, I'll come back to that in a minute, we could collect the products and measure the percentages of each of these species, plot them. Now at some other point along in here, we have the second pulse, and the third pulse, etc. Now, if one plots 1 over the pulse number and connects the points, you have a beautiful series of curves with 2 or 3 maxima that occur. And these are things that our students do now as a part of an undergraduate experiment. This is an interesting way of measuring the A to B to C type series reactions that occur. Only in this case, we're talking about benzene only, but with different isotopic species. So, and just to look at the statistical exchange for a moment, the statistical distribution we get depends on, of course, the number of ways that one can distribute hydrogen and deuteriums around the molecule. If we have all hydrogen in the benzene, there's really only one way to have the D0 species. The same thing is true for D6. It's either all hydrogens or all deuteriums. But when one puts into it 1 deuterium or 1 hydrogen, there are 6 different ways that we can put them, 6 different places. And so that takes care of these two, the D5 and the D1. Now for D2, let's say it's a little more complicated. Let's say we fix the first one here. We have now 1, 2, 3, 4, 5 new places where we can put the second deuterium. Now if we scratch that one and move up here for our first one, we have now 1, 2, 3, 4 new positions. And finally, we have 3, 2, and 1. If we add all of those together, it turns out that there are 15 different ways that we can have 2 hydrogens or 2 deuteriums in the molecule. For 3, the number is 20. Here we have 15. So that's the kind of distribution we would get. Those can be normalized, and they give the distribution we have on the right. And if one looked at the mass spectrum, we would have peaks that, in fact, mimic these things after one has made corrections for the carbon-13 isotope peak. This would be 78, 79, 80, up to mass 86, or 84, I'm sorry. So anyway, that's exactly what it looks like, and it should, based on this simple time of exchange. So we can then count, if one has not an H to D ratio of unity, but an H to D ratio either greater than or less than 1. Supposing it's greater than 1, there would be a distribution shifted to the left. Or if it were less than 1, the distribution would be shifted to the right. And all of those things can be predicted, and it's shown that the data that one obtains are very close to the statistical equilibrium that one would calculate based on this sort of thing. Now, let's come back to this alkyl versus aryl hydrogen exchange. I mentioned in the Q-mean that only the aryl hydrogens underwent exchange, the aromatic hydrogens. This can be shown by operating at a temperature somewhere around 150 degrees C. where one has essentially no dealkylation. And one can begin with a mixture of deuterated benzene to cumene, but operated under a point where there's no cumene reaction except for exchange. And if one has a large excess of deuterium, deuterated species in here, now we can collect both the benzene and the cumene that come out. And what we started with, of course, was benzene, which is the open squares here. Benzene was 100% D6. And the cumene was, of course, completely hydrogen with no deuterium in it, would be down here to the left. Well, when you pass that mixture in a pulse over the catalyst, 1 second contact time again, this is the kind of distribution that one obtains. Now, part of the deuterium has now picked up some, deuterated benzene has picked up some hydrogen, indicated by the blue lines here. So we have a shift in this direction. But the cumene, which started over here, has shifted in this direction, and notice that it stops at D5. Now, there are 5 aryl hydrogens and 7 of the alkyl hydrogens. There is essentially nothing. There's just a little tiny bit of D6 material from the benzene, or from the cumene. If one were to have had complete exchange, one would have had a distribution that looks something like this. And as you can see, there's no correlation whatever. So only the aromatic hydrogens and the olefinic hydrogens on the propylene product exchange, not the alkyl group, as long as it's attached to the cumene. And this is probably what we would expect if we were to put this material into deuterated sulfuric acid. The same sort of thing occurs. You would have very rapid exchange with the aryl hydrogens, but not with the alkyl hydrogens. Now, a question that one could ask about the cumene reaction is it simply, are we looking at equilibrium? Could we have just simply, by changing the well, I didn't go into this, but by changing the temperature, of course, one can get an activation energy for the cumene reaction. But one could also say that all one is seeing is the shift in conversion, equilibrium conversion with temperature. And of course, it's made by alkylating benzene over an acid-type catalyst. And in this case now, we're looking at the reverse reaction where cumene goes to the benzene and propylene. And the equilibrium constant for this reaction is such that depending on the total pressure of the hydrocarbons that we had, we would have different degrees of fractional conversion at equilibrium. As the pressure goes up, say at the temperature that we were using, I think this was calculated about 350 degrees centigrade, that at a high pressure of the hydrocarbons, one could have at most only 34% equilibrium conversion. However, if the pressure were small, then the equilibrium shifts to the right and one could have almost 90%. But can we test this under conditions where we were actually doing some of the reactions, the dealkylation reactions? And the answer is we can test that by starting with a mixture of cumene and a very small amount, say the order of 1 or 2%, highly radioactively labeled benzene. And in this case, if one looks at the specific activity, the benzene will fall off as one changes the flow rate and has higher and higher conversions. And that's because we're diluting the radioactivity of the benzene with the material coming from the cumene. But the important thing is to look at the radioactivity in the cumene, which could get there only by the reverse reaction. And the answer is that there is essentially no radioactivity in the cumene until we get out beyond about 70% conversion. And at that point then, you do begin to see some of the reverse reaction taking place. So we are not at equilibrium. In fact, these curves will come together at some point when we get to equilibrium. That would be somewhere around 95% conversion. So that gives one an idea of what the concentration of the hydrocarbons are in the presence of the catalyst. Now this is carried out in a helium carrier gas stream where the absolute pressure was about 2 atmospheres. So there's a possibility that the hydrocarbons, when one puts a pulse in, simply displace the helium. And so the maximum concentration that one could have would be about 2 atmospheres. Well, obviously at 2 atmospheres that would be a very low conversion. So here we certainly do not have that condition. My guess is that when the pulse goes in, that the hydrocarbon amount is only a very small, low partial pressure, and we're certainly not having the total partial pressure being equal to the helium carrier gas concentration. So this is a nice way of using the radioactive tracers to tell whether or not reactions are reversible under these conditions. Well, now let me change to the second reaction that I'd like to talk about. And we have a very different result because we're talking about temperatures now in the room temperature range. Here, whereas the hydrogens that were on the surface, or in the other case where they were extremely rapidly exchanged at 350 degrees, at 25 degrees, they are not. And the test reaction that goes easily in the room temperature range is butene isomerization. And here again, we have the formation of a carbonium ion, probably, and then we have the completion of the reaction to form, say, going from 1 butene to the 2 butene product. Now, the carbonium ion that's formed in here may possibly have a structure that looks like this. And here we have added the proton to form the carbonium ion, and the second carbon would be this one right here. This thing may have an interesting structure where it's one could envision being relatively parallel to the surface. That the C1, 2, and 3 are forming a material that's parallel to the surface. If that were true, then the methyl group over here would be sticking away from the surface, and there are 2 hydrogens, one of which has to be lost to form either the cis or the trans 2-butene. Now these 2 hydrogens are identical chemically. They're both secondary carbon-hydrogen bonds, should have relatively similar energetics. However, geometrically they're quite different. If one removes the hydrogen here, then the methyl group would have a tendency, by the principle of least action, to fall in a direction which would make it cis to the carbon 1. On the other hand, if this hydrogen were lost, it would probably fall to the other direction, which would form trans complex, or trans isomer. And it happens that over these catalysts in this temperature range, the cis to trans ratio from 1-butene isomerization is essentially unity. And moreover, it is not temperature dependent, which you wouldn't expect if these 2 have similar activities. Now, on the other hand, we could form the same kind of complex by starting with either cis or trans 2-butene and adding a proton to this position to form the same carbonium ion. But here, if you lose or take away the same hydrogen that was put on the surface, say we started with trans, it would be this hydrogen right here. If we remove that hydrogen, we have no reaction because it would go back to the trans isomer. However, if we lose this hydrogen, we would have the cis isomer. But if one loses one of the hydrogens on the methyl group, then one would form the butene 1. So it looks statistically like we have 3 times as many of the methyl hydrogens as we have the hydrogen A. So this means statistically that one should have 3 times as much 1-butene form as the cis 2-butene starting with trans. Well, that's not what happens. Actually, one ends up with only about 7,5 as opposed to 3. And so this can be explained, though, by the fact that the carbon-hydrogen bonds are stronger bonds in the primary configuration than they are in the secondary. And there is a known difference in bond energy between these 2, and when one factors that into the accounting for this, then it turns out that this bond being more difficult to break does in fact occur only about 1/4 as often as this, and 3/4, 1/4, or 3 times 1/4 gives us the 0.75. So here we can, when we bring energetics into the picture, account for pretty much the butene 1 to cis ratio starting with the trans molecule. And the same thing can be true if one starts with cis and goes to 1 butene to trans ratio. So those things can be accounted for. And again, the tracers indicate that this is what indeed happens. If one has a mixture now, a 1-to-1 mixture of deuterated butene to hydrogenated butene, and if one now adds either a hydrogen or a deuteron from the surface, half the time if you have a mixture you would add a hydrogen, half the time a deuteron. So if we start with a mixture that's 50-50 D0 and D8 butene, the products, if this reaction is occurring, should be 50%, or actually 25% of each of 4 isotopes, one where you picked up an isomer or an isotope of the same type molecule, say in this case a hydrogen, or if the hydrogenated species picked up a deuterium, one would have this, and just the opposite is the case here, hydrogen and deuterium. And that is in fact what's observed. You have about 1/4 of each of those 4 isotopic species. So on the average it looks like that you're exchanging half an atom per molecule, but that's only because you have half as many of the different kinds of isotopes. Now, there's a question now about the source of the hydrogens on the surface. In the past, we had said with the cumene dealkylation that the source was in fact the deuterons on the surface that were associated with the catalyst itself. But that was at 350 degrees. Now at 225 or at 25 degrees C, something much different happens in the case of butene. When one puts a pulse of butene over the catalyst, in the first place, you don't get it all back. Part of it is irreversibly adsorbed as a carbonaceous residue or coke. And if one adds this thing, say radioactively labeled carbon-14 1-butene in the first pulse, one lays down a carbon-14 material with hydrogens in it. Now, if one puts a second pulse of deuterated butene over the catalyst, well, I should mention that there is no deuterium in the product from this first pulse. Now, if one puts a second pulse over the catalyst, one now does, of deuterated butene, one does see hydrogen in the product, but no carbon-14. So what is happening here is that probably these very acid hydrogens or deuterons on the surface, in fact, are so active that they have polymerized the butene into a carbonaceous oligomer of some type. And this oligomer now is providing the active sites for the steady state reaction that would occur. And one could repeat this afterwards. Once this residue is laid down, then it does not increase that dramatically. The first layer is the one that's most important. So the source then seems to be not the original deuterons on the surface, but the induced sites, which are less acidic than certainly would be these original ones down here. So acidity is important, but if you have too much, it can polymerize things instead of simply carrying out the isomerization reaction. Now I'd like to switch to another type of reaction, this being the oxidative dehydrogenation, where we have still different type behavior. We're looking at ferrite catalysts here, and if one starts with a normal butene, one can dehydrogenate by using chromia catalysts and iron oxide catalysts to make butadiene plus hydrogen. But this reaction is thermodynamically limited. And in the region now, we're back up at high temperature, 300, 400 degrees centigrade. The equilibrium constant is not favorable. So you have to go to higher temperatures in order to carry out the simple dehydrogenation to form the butadiene. However, if one adds 1/2 oxygen to this and removes the hydrogen as water, then the equilibrium constant goes from unfavorable to irreversible, 10 to the plus 10. But unfortunately, anytime one mixes oxygen and hydrocarbons, one is liable to get the CO2 in water, which has an equilibrium constant of 10 to the plus 210 at these temperatures. So the reaction, of course, would be totally combustion if thermodynamics alone were controlling. But with the proper catalyst, and the one that I've mentioned is a magnesium ferrite and other ferrites, one can have good yields of the butadiene and water product. Now, one thing that's interesting here, even though we're at 350 degrees or so or higher, still there is no isomerization of the butanes. Now, if this were an acid catalyst, which would I do this at room temperature, we would have extremely fast butene isomerization. We do not over these catalysts. And secondly, if one takes a mixture of C4H8 and C4D8, let's say in ratio of about 1 to 1, then there is no scrambling of the carbons and hydrogen. One ends up with D6 and H6 butadiene. No scrambling, which is quite different from what was observed with acid catalysts. And moreover, the ratio of the products of the heavy material to the light material is about 1 to 2.5. So in other words, we have a very large primary kinetic isotope effect at this temperature. In fact, this looks like then the reaction must occur by cleavage of the carbon-hydrogen bonds to form butadiene, and that this cleavage is rate limited. So one might ask then, where do the hydrogens go? And we think that the hydrogen goes on oxygen atoms that are at the surface of this, and we form hydroxyl groups. Then these hydroxyl groups, of course, can condense to give us the water product, and then oxygen from the gas phase can come back down and replace it. So I'm going to skip a part of this now and move on to looking at the oxygens, again using isotopic tracers. Only this time we'll use oxygen 18 to try to find out how many of the oxygens participate in the reaction. And one can, again, this time, instead of using oxygen by itself, which is difficult to track and collect, one could use CO2 labeled with oxygen 18. And if one plots over here the exchange of the oxygen 18 CO2 with the oxygens on the surface, one, of course, finds that they do mix, and that the oxygen 16 from the surface then is replaced. And if one does the same thing that we did with the hydrogens by plotting 1 over the total number that it exchanged as a function of reciprocal pulse number, that we have a series of curves at different temperatures, all of which will come in to about the same point, which is 1 over sigma infinity, the total number of oxygens that are undergoing this exchange. And this number right here is approximately equal to 1 monolayer of oxygen that's exchanged. So we feel that we have only very slow exchange of subsurface oxygen, involvement of subsurface oxygen in this, that it's mainly a surface oxygen that is involved, and also the oxygen 18 that has been put on the surface can be replaced with oxygen 16 to a fairly quantitative degree. Now, if one goes to higher temperatures, of course, than the 350 degrees or so, then you can exchange bulk oxygens, but not under these conditions. So let me quickly move on to a mechanism, and then I'm going to quit with this. to look at the oxidation reduction type mechanism, if one begins with a reduced iron oxide or magnesium ferrite, which has the iron in it, we believe is the iron Fe plus 2 plus 3 couple that is the oxidation reduction couple. If we begin with, say, if we could imagine that this is at a corner of a crystallite, if one continued the crystal on in the vertical direction, one would have another iron or magnesium site. If one went in the other direction, one would have an oxygen, but neither of those sites is occupied. So we have vacancies, and we call the open circles the anion and cation vacancies. And so oxygen then can come from the gas phase and can be adsorbed on the anion vacancy, and then an electron transfer occurs and we oxidize the surface to Fe plus 3, and we have an adsorbed oxygen atom. Now in the cation vacancy, the C4H8 can be adsorbed, C4H8, and this can be adsorbed and desorbed many times, but on one of its trips to the surface, then we have the formation of C4H7 through the cleavage of one of the carbon-hydrogen bonds. And that reaction is a rate-limiting step, because we know that from the isotope effect. So I could go ahead and write the other things that go from the C4H7 to C4H6, which give us our butadiene product. And then we have oxygens. By the way, the hydrogen that comes off would probably go on this forming an hydroxyl group, and the hydroxyl groups can be condensed to come off to get the other product, and we have an oxidation reduction system that's taking place with a clockwise movement over here. But the point is that I wanted to make is that by using the isotopic tracers, we know that it is in fact the surface oxygens that are involved in the catalytic reaction. We know that there's a rate limiting step, and the cleavage of the carbon-hydrogen bond is involved in that step. And then we have what looks to be a very complicated reaction. It's in fact fairly simple reaction, as opposed to the reaction with cumene, where we have massive amounts of statistical exchange between the hydrocarbons and the hydrogens on the surface. So with that, I'm going to quit. Thank you very much.
We have time for perhaps one question, if there is a short one. Yes.
Your tracers work assumes mostly no isotope effects on the hydrogen deuterium.
The scrambling part does, yes. And only in the case of the oxidative dehydrogenation was there a significant observed isotope effect on the carbon-hydrogen cleavage. That is correct.
The temperatures are very high, so that seems very reasonable.
Yeah, but even at 350 degrees, to get a 2.5 kinetic isotope effect, that is an enormous isotope effect. In fact, one even wonders if that's theoretically possible. There's some question about that.
It is.
Thank you, Jeff.